Hi, this is week 25 of AP Physics, and we're going to go ahead and start Unit 7, which deals with torque and rotational motion. For our agenda for today, we'll be looking at torque and equilibrium as well. For our lesson objectives, students will learn how the length of a lever arm affects torque, and students will also learn how torque affects equilibrium. So let's get started.
So we're going to go ahead and begin our conversation about torque by going over the definition of what is torque. A force that causes angular acceleration is known as torque. The effectiveness of the force is determined by three things: the magnitude, the position, and the angle applied to the force. All right, talking about the magnitude is how much force you're pushing on the object to create torque. The position is how close or far away are you from the pivot point where the object is turning, and also the angle. Ideally, you want to go ahead and apply force at 90 degrees, but sometimes that's not possible. Perhaps you're working on loosening a screw inside of the engine compartment in a car and you don't have the proper angle. Ideally, like I said, you want 90, but sometimes it's not possible. So the angle also plays a role. All right, so torque is calculated by this formula right there. We have torque is equal to R times F, where R is how far you are from the pivot point where it turns, and F is the force. Now this formula is when the force is perpendicular to the object. So force acting on an object, which is F, and the position of the force, which is R, are both vectors. So you got to keep in mind they're positive and negative signs. Now torque is calculated using the following formula when it is at an angle. So it's torque is equal to R times F multiplied times sine of theta. So if the force is at an angle other than perpendicular, you're going to use that formula right there. Now the distance from where the pivot point happens and where the force is being applied, that's referred to as the level arm, which is R times sine theta. Now let's go ahead and move on to our first example.
In example 1, we're asked the following question. Two disgruntled business people are trying to use a revolving door. The woman on the left exerts a force of 625 newtons perpendicular to the door and 1.2 meters from the hub center. So let's go ahead and write that down. The force of the woman, it is 625 newtons, and the radius of the woman is negative 1.20 meters, negative because she is to the left of the pivot point. Next, they give us the following. It says, while the man is on the right exerts a force of 850 newtons. So force of the man is equal to 850 newtons, and he is positioned at 0.8 meters to the right of the pivot point. So there we have it. Next they ask us, can you go ahead and figure out what is the net torque? So our strategy is going to be to find the torque of the woman, then the torque of the man, and then put them together to get the net torque. Alright, so let's begin. Formula for torque is radius times force. So there we have it. Alright, so now we're going to go ahead and multiply both of these to get the torque of the woman. So that's going to go ahead and give us 1.2 meters multiplied times 6.25 newtons. Put it into your calculator and you get 750. That's the torque, negative 750 newtons times meters. Next, for the man, it's going to be 0.8 meters multiplied times 850 newtons. And we're going to get for the torque of the man 680 newtons. Alright, now we got them both. We're going to go ahead and put them together to get the torque net. So that's going to go ahead and be torque net is really just the torque of the woman plus the torque of the man put together. So for the woman it was negative 760 newtons times meters plus 680 newtons times meter for the man. So that goes ahead and gives us negative 70, and that is the net torque. Alright, what does that mean? It means that on the negative side, she's going to be able to exert more torque, so she will actually be able to go forward as the man is being pushed back by the hub. Alright, so that takes care of example 1. Now, for problem number 1, they ask you guys, what happens if the woman suddenly slides closer to the hub by 0.4 meters? So she was at 1.2, so let's take away 0.4 meters because she's going towards the left. So now she's going to go ahead and be, instead of 1.2 minus 0.4 is going to give us 0.8 on the left hand side, 0.8. Notice that's the same as the man. So now both of them have the same distance from the pivot point. So, but the man's got more force, so therefore he's going to be able to exert more torque. So now, in this scenario where she slides closer, he is going to be able to go forward while she'll be pushing back because he's exerting more torque on the revolving doors. So that's what's going to happen in problem number 1. Next, problem number 2 says a businessman enters the same revolving door on the right, pushing with 576 newtons of force directed perpendicular to the door at 0.7 meters. All right, so let's go ahead and plug in all the information that we've got for this next problem. All right, and his force is 576 newtons, and he is to the right at 0.700 meters. Next, a boy enters, exerts a force of 365 newtons perpendicular to the door at 1.25 to the left of the hub. So it's going to be less force, but he's further away. He's on the left side, so I'm going to put a negative because he's on the left side of the hub. For part A, they said, find the torque exerted by each of the individuals, the boy and the man, and the net torque as well. That's part B. So let's go ahead and do that. Part A will be here. So we just got to multiply both of these because torque is just R times F. So the force times the radius. So let's do that for the boy. So I'm going to put that B. It's equal to negative 1.25 meters multiplied times 365 newtons. All right, and that's going to go ahead and give us the following answer. 365 times 1.25 gives us, we're going to round it up slightly, 456.3 newtons times meter. All right, for the man, the torque on the man is going to be 0.700 meters multiplied times 576 newtons. So 576 times 0.7 gives us 403.2 newtons. Alright, so in part A it says solve for the torque of each one. Here's the torque of the boy, here's the torque of the man. Notice that the torque of the boy is greater, so he's going to be able to push the revolving doors his way, and while the man's being pushed backwards. Now, part B they say, can you go ahead and solve for the net torque? So let's go ahead and do that. Net torque is going to be, if you just add them up, the torque of the boy plus the torque of the man. So let's go ahead and do that. He is at negative 456.3 and he is at 403.2. So it's going to go ahead and give us the following answer. Negative 53.1 newtons times meters, and that will be the net torque. As we stated, the boy will be able to push the hub forward in his direction as the businessman is being pushed back. That takes care of problem number 2. Let's go ahead and take a look at example 2. In this example, you ask the following. For part A, a man applies a force of 3 times 10 to the 2, or 300 newtons, at an angle of 60 degrees at 2 meters from the well-oiled hinges. So we have our door right here. There's a knob 2 meters away. He's applying the force at an angle of 60 degrees, 300 newtons of force. Find the torque on the door, choosing the position of the hinges as the axis of rotation. So that's part A. Alright, so what we're going to go ahead and do is use this formula now, because the man's not applying the force perpendicular, so he's applying it at an angle. The angle is 60 degrees. So now that goes right here. So all we got to do is go ahead and substitute the numbers in to get the torque exerted by the man, where the R is how far he's exerting it at 2 meters. The force he's exerting is 300 newtons, multiplied times sine of the angle he's exerting the force at, 60 degrees, and that's going to go ahead and give us the answer for what is the torque. That is part A. So let's see, sine of 60 degrees multiplied times 300 times 2 gives us a grand total of torque of 520 newtons times meter, rounded that off slightly. So that will be the answer for part A. In part B, we're asked the following question. Suppose that the wedge is placed 1.5 meters from the hinge on the other side of the door. What is the minimum force what minimum force must the wedge exert so that the force applied in part A won't open the door? Alright, so we're exerting this force, this torque in part A. Alright, so what they want to know is, alright, how much force does that wedge need to do? But the wedge, notice that it's closer to the pivot point, to the hinges of the door. Alright, so it's going to need more force than the 300 newtons. Alright, so how much would it need? Alright, so it's going to need the same amount of torque in the opposite direction. So for part B, we know we need this. From the wedge, it's going to need negative 520. Negative because it needs to apply torque in the opposite direction, but equaling magnitude, but opposite in direction, so therefore it won't open. Now, we know that torque is equal to R times F, and now the wedge is going to be perpendicular to the door, so we don't need the sine theta. Alright, now we know that we want the wedge at 1.5 meters from the hinges, so that's going to give us how much force it's going to need to apply. So that's really going to be torque over radius. That's going to be how much force we'll need. Alright, so for the force is equal to torque was negative 520 newtons times meters divided by the radius, which is 1.5 meters from the hinges of the door. So we go ahead and put that in a calculator. That's going to give us the force needed. Alright, so it's 520 divided by 1.5 gives us negative 347 newtons. Negative because it's in the opposite direction of the force applied by the man. Alright, so that will be the answer for part B. Let's go ahead and move along next to problem 3. To make the wedge more effective in keeping the door closed, should it be placed closer to the hinge or closer to the doorknob? Alright, so if you look at our formula here, this is a distance from the pivot point, in this case the hinges of the door. Alright, notice how it is in the numerator, so therefore it's going to be proportional to the torque. So in reality, you want the larger the R, that's going to give you the larger the torque, and you want more torque. So therefore, the answer would be further away from the hinges, so therefore closer to the doorknob. And that's going to go ahead and make it the most effective possible at keeping the door closed. Now let's take a look at problem number 4. In this one, it says a man ties the end of a strong rope that is 8 meters long to the bumper of his truck, and it is 0.5 meters from the ground. So that's the attachment point. From the bumper to the ground is 0.5 meters from the ground, and the other end of the is attached to a tree trunk at a height of 3 meters. It says he uses the truck to create a force tension of 800 newtons in the rope. Compute the magnitude of the torque on the tree due to the tension of the rope, with the base of the tree right here acting as the reference point. Alright, so the 3 meters is going to be, there's your reference point, that's where the tree is going to pivot, and that's where the force is being applied. Alright, so to solve this problem though, we need to know at what angle is this force being applied. So we're going to go ahead and draw a right triangle right here, and we're going to go ahead and try to figure out what is that angle right there. After we have that, we can go ahead and easily just put it to figure out here into this formula. We have the R, which is from the pivot point to where the rope is applied. That's 3 meters. We have the force, 800. So what we really need is the theta. What is this angle right here that the force is being applied on? Alright, so let's go ahead and figure that out. We know the hypotenuse has a length of 8. What about from this point to that point? We know from the ground and up is 3 meters, but from here up, that is where the ropes are tied, that is 0.5. So that's going to be 2.5 meters. That'll be that distance right there. So now we have the adjacent and the hypotenuse, so we can go ahead and figure out that angle. So it's going to be cosine of theta, that's the angle that we're looking at, will be adjacent, which is 2.5, over the hypotenuse, which is 8. Alright, so that's what we're going to go ahead and do to figure out the angle at which we're applying the force. So it's going to go ahead and be 2.5 divided by 8 gives me 0.3125. And next I'm going to go ahead and do inverse cosine to go ahead and figure out the angle. So that gives me 71.7 degrees. Alright, so that's going to be our angle. Now we can go ahead and figure out the torque being applied on the tree, which is 3 meters high, total force of 800 newtons, and sine of 71.7. Alright, so we plug all of this to a calculator and we'll know how much torque is being applied on the tree. So it's going to be sine, our answer, which is 0.949 multiplied times 800 multiplied times 3 meters. It's going to go ahead and give us a total torque. We're going to round it up slightly, 2,280 newtons per meter. And that is your answer for problem number 4. In example 3, we're asked the following question. A woman with mass of 55. In example 3, we're asked the following question. A woman of mass 55 kilograms sits on the left of a seesaw with a plank length of 4 meters, pivoted in the middle. So her mass is 55 kilograms and she sits 2 meters away from the pivot point. The whole plank is 4 meters long, so she's halfway. The pivot point's at the middle, so she sits 2 meters to the left of it. So I'm going to go ahead and put -2 because she's on the left. So this is her mass. That's how far she is. Next, the problem continues and states, first, compute the torques on the seesaw about an axis that passes through the pivot point. Where should the man of a mass 75 kilograms sit if the system is to be balanced? They're in equilibrium. So how far should he sit? Alright, so we're going to go ahead and do that. It's in equilibrium, so therefore the torque of the man equals the torque of the woman since they're balancing each other, right? So we're going to write that down. Torque of the woman is equal to the torque of the man, magnitude. Alright, next, we're going to go ahead and say then that torque is equal to R times F. This is for the woman, so I'm going to put WW. And for the man, R, M, multiplied times Fm, which is the force of the man times the radius of the man. And that's what we're looking for. How far from the pivot point should the man be sitting? Alright, so how do we get the force? Well, the only force that's acting on them is really force of gravity, pulling them down. So force of gravity is mass times gravity. So I'm going to go ahead and put this down. Rw times mass of the woman times gravity is equal to Rm times mass of the man times gravity. Alright, so at this point we're looking for Rm. So we're going to go ahead and divide both sides by these. Mass of the man times gravity. So that way we can go ahead and isolate the radius, how far he should be from the pivot point. The distance, actually, the lever arm. Alright, so notice also that G goes away. So there's our formula. It's just really the radius of the woman times the mass of the woman divided by the mass of the man. And that's going to tell us how far the man should be sitting. So that's going to be our W. She's at -2.0 meters. And we're going to go ahead and multiply that times her mass, which is 55 kilograms, and divided by his mass, which is 75 kilograms. And that's going to go ahead and give us our answer. Now he's sitting on the other side, so it's going to be positive. So it's going to be 55 times 2 divided by 75. It's going to go ahead and give us a 1.47 meters. That is how far he should be sitting from the pivot point. So that is part A. In part B, they asked us to find the normal force exerted by the pivot point on the plank that has a mass of 12 kilograms. Alright, so now we have the man, the woman, and now the plank. So how much normal force is exerted by the pivot point? If you go back to the picture. So right here, how much normal force exerted by the pivot point if it's holding the man, the woman, and the plank as well. Alright, so let's get the total mass. The total mass, so this is part B, mt is going to be the mass of the woman plus the mass of the man plus the mass of the plank. Alright, so that's going to go ahead and be the following. It's going to be 55 kilograms plus 75 kilograms plus 12 kilograms from the plank. Alright, that was given to us right there. Next, what's the total? 55 plus 75 plus 12 gives us 142 kilograms. That's the total mass. Alright, so how much force are they exerting due to gravity? Is going to be mass times gravity. So force due to gravity is going to be 142 multiplied times acceleration due to gravity negative 10 meters per second squared. So that's going to go ahead and be negative 1,420 newtons. So therefore the force normal is going to go ahead and be just the same in magnitude, opposite in direction, 1420 newtons. And that is your answer for part B. That takes care of this example 3. Next, let's go ahead and move along. And this one says, what happens if the woman now leans backwards? Will they be able to achieve equilibrium? Alright, now, as she's leaning backwards, she's sitting in the same spot, still at 2 meters. She's sitting, but she leans backwards. So now her center of mass is further away from the pivot point. So, let's bring up the picture. As she leans backwards, her center of mass moves further away, giving her more torque. Now she will go down and he will go up because she leaned backwards, moving her center of mass further away from the pivot point. So that's what would happen. She would go down, he would go up. They're no longer in equilibrium. Alright, let's go ahead and move along to the next one. Now, in this problem, problem 6, they ask you, suppose a 30-kilogram child sits 1.5 meters to the left of the center of the same seesaw. A second child sits at the end of the opposite side, and the system is balanced. Find the mass of the second child. Alright, so let's go ahead and do that. We got 2 children sitting on the seesaw. We need the mass of one of them. Alright, so let's erase all of this. So we have one kid who is at 1.5 on the left hand side. I'm going to go ahead and put negative 1.5 meters. And he has a mass of 30 kilograms. On the other side is his friend. We're going to switch them, call them 1 and 2. And he's his friend, and he sits all the way to the end on the opposite side. So that is sitting at 2 meters. And they want to know, what is the mass of the second child? Alright, now we do know this, that this boy is closer and has a mass of 30. So therefore, for this boy to be further away and still be in equilibrium, therefore he must have a smaller mass. Alright, so now they're in equilibrium, so the torque of number 1 equals the torque of number 2. Boy 1 and boy 2, they equal each other out, right? So next, we're going to go ahead and put what is torque. It is R times F on both sides. 1, 1, 2, 2. So there we have it. Next, what is the force? So the only force that they have is force due to gravity, so it's mass times gravity. So I'm going to put R1 times M1 times gravity is equal to R2 times M2 times gravity. And we're looking for M2 in this scenario. What is the mass of our second child? So we're going to go ahead and divide by R2 times G on both sides. R2 times G. The G gets canceled out on both sides. So M2 is really R1 times M1 over R2. That will be our formula. Let's go ahead and plug in the numbers. So it's going to be negative 1.5 kilograms. Multiply times the mass, which is 30 kilograms. Over R2. R2 it is going to be 2 meters. Alright. And pardon me, that's not kilograms. That is meters. And there we have it. Alright, the negative. He doesn't have a negative mass. We're going to go ahead and drop that. With the negative just there to signify that the boy's on the other side of the pivot point. Alright, so now we're going to go ahead and multiply 1.5 times 30 divided by 2. So it gives us a mass of 22.5 kilograms. Yeah, the boy was lighter than his friend who had a mass of 30. Alright, that takes care of part A of this problem. In part B, it says find the normal force acting on the pivot point against the same seesaw. So we would add up their masses. So now we know that the total mass, MT, is going to be the mass of boy number 1, which is 30 kilograms, plus mass of boy number 2, which is 22.5 kilograms, plus the mass of the plank, which was 12 kilograms. So to get the total mass, that's going to be 30 plus 22.5 plus 12 is going to give us 64.5 kilograms total. So what will be the force due to gravity? It's going to be mass times gravity. So it's going to be force due to gravity. It's going to be negative 645 kilograms. So therefore, force normal is going to be positive 645, not kilograms, newtons. Alright, that will be part B, and this is part A. And that takes care of problem number 6. Up next, let's take a look at problem 7. They tell you guys the following. It says an object rotates with an angular speed that varies with time, as shown in the graph here. How can the graph be used to determine the magnitude of the angular acceleration, alpha, of the object and justify your selection? Alright, angular acceleration is going to be the following. It's going to be here, notice we got angular speed over time. And angular speed over time is going to be the angular acceleration. So therefore we have to divide them. So that's rise over run. So to get rise over run, that means we need to find the slope of the line. So the answer for this problem would actually be B. Determine the slope of the line from 0 to 2 seconds, because the slope of the line, rise over run, equals that angular acceleration. Alright, that takes care of that problem. Let's go ahead and now take a look at problem number 8. In this problem, they go ahead and they ask us, says, a graph of angular velocity as a function of time is shown for an object that rotates about an axis. 3 time intervals, 1 through 3, are shown. Which of the following correctly compares the angular displacement theta, delta theta, for the object during each time interval? Alright, so there's the graph right there. And again, this is your angular speed over time. Alright, now, if you wanted to go ahead and solve for angular speed, that is equal to angular displacement over time. So in this problem, though, we're asked to solve for the angular displacement. So how will we isolate the theta? We'll multiply by t on both sides. Alright, so that will give us this. So to get the angular displacement, it's going to be time multiply times the angular velocity. Alright, when you multiply them, that means that you need to find the area under the curve or under the line. Alright, so which one of these look the same? Alright, that matches the areas. Alright, so I know that the area under part 1 and part 3 look the same to me. So those two are identical, so that one already looks good to me, but so does A. But notice the area under 2 is larger. That is larger than 1 or 3. So 2 is larger. So answer B looks really good, where it says theta 2 is bigger than theta 1 and 3, and theta 1 and 3 are the same. So again, we're looking for the area under the line, and B would be the correct answer. Let's go ahead and move along to our next problem. So for this problem, they go ahead and they ask you, the graph shows the angular velocity as a function of time for a point at a rotating disk. The magnitude of the angular acceleration of the disk at time 2 is most likely, alright, so time 2, notice it's a straight line. Alright, so again, they're giving us angular acceleration over time. But in this case, they don't want angular displacement like they did in the previous one. They want angular acceleration, which is angular velocity over time. That means they're divided. So therefore, what do we want? We want the slope of that line. And it's a straight line, so really the slope at time 2 will be the same as the slope at time 3 as time 4. Does not matter. But let's go ahead and figure out the slope of the line. So let's get the initial and final point. So that's going to be 8 minus 2 on the numerator. 8 minus 2 over here 4 minus 0 for this point, 4 and 0. So it's going to go ahead and give me a 6 over 4. Alright, so that's going to go ahead and give me a 1.5. 1.5. So the answer would be letter B in this scenario. And that takes care of this problem. This also brings us to the end of this lesson, and thank you so much for watching.